Hey there, hope you were doing great. I am. It's a beautiful day outside and I'm feeling good today. So, let's get into it. Today in this video, we're going to talk about stacks. Stacks are a really cool data structure that are used basically everywhere. Quick sources, you've probably seen these before. You got the Project Full Stack GitHub, where all the code's going to live. I got Wikipedia for some random definitions and whatnot. Big O cheat sheet for some time complexity diagrams, and Visual Go for some animations. But what is a stack? So a stack is a abstract data type with basically two principal operations, pushing and popping. So pushing means we're going to go ahead and we are going to push or add a new item to the top of the stack. Pop is when we remove an item. Little spelling mistake there, it says stack. Should say stack, but pop is when you remove the top item from the stack. So you'll notice both of these right here operations, pushing or popping, are manipulating the top of the stack. And with that principle, we get this ordering scheme, if you will, called last in, first out. Which means anytime I add something to the stack, whatever I added last is going to be the first thing that I'm going to remove, because we push to the top of the stack and then we remove from the top of the stack. So the last thing I insert is going to live at the top of the stack, so it's going to be the first thing that I remove, which is this concept, last in, first out, or LIFO. You'll probably hear me say LIFO. All right, here's our time complexity. It's very good for insertion and deletion. Accessing or searching are O to the N, because you'd have to do it linearly, except we don't really do this with a stack. With a stack, the only operations we honestly really care about are these right here, the insertion and deletion. And you can see it's O to the 1. We're either going to push things to the top of the stack or we're going to remove things from the top of the stack. We're really not going to use a stack for any type of searching or any type of, individual accessing specific indexes. So all we're doing, inserting and deleting, you can see it's very good for time complexity. All right, so here's how it works. Last in, first out. You always add to and remove from the top of the stack. So this is my little kind of diagram here that represents a stack in memory. I got the top of the stack. Right now this thing's empty. There's nothing in there. If I want to add something, such as this little blue node, if you will, we put it at the top of the stack. So I have this little pointer here, saying, hey, this is the top of the stack. Just a little bit of terminology as well. We normally call the bottom of the stack the base. However, that's not super important because we don't necessarily really care about it. The biggest thing we care about is what is at the top of the stack. And then to add a new thing, remember, we're going to add to the top of the stack. So if we add a red node, now the red node's going to be at the top. The pointer for the top of the stack is going to point to the red node, and now the blue is at the bottom. So if I were to remove this, the first thing that'd be removed is the red node, and then the blue node after that. And you just keep following that. We're going to add another node, a purple node. It gets pushed to the top of the stack. We're going to add another node, a green node, and it gets pushed to the top of the stack. Pretty simple concepts there. We're always going to push to the top of the stack. Okay, to remove, like I said, we're always going to pop or remove from the top of the stack. So the last thing I added was this green node right here. Because it's the last thing I added, it's at the top of the stack, I'm always going to remove from the top of the stack. So on the next slide here, if I could get to it, there we go. We popped out that green node. And then now what's at the top of the stack? The purple node. So if I were going to remove from the top of the stack again, I'd get the purple node, and all of these elements, the red and the blue, would basically shift themselves up just like that. If I pop again, we're going to remove from the top of the stack, which is red, and the blue gets shifted up. If I were to pop again, there's only one element left, but it's the top of the stack, and we remove the blue. So even though the blue was inserted first, all the way back here, right? It's the very first thing we added to our stack. It was also the last thing that we popped. Last in, first out, LIFO, right? So that's how it works. The last thing we put in is the first thing we pull off. We're always pushing to the top of the stack and popping from the top of the stack. To look at it in Visual Go, you'll notice that it's in Visual Go here, it's underneath the list. So if I go to Visual Go here, It'll be underneath the linked list, I believe right there. Yep, and you can see, let me disregard these, you can see right up here, stack. All right, the reason it's under linked list is because you can create a stack out of a linked list data type. You can also do it out of the built-in Python list or an array. So two separate ways to do it, but a lot of times you'll use a linked list. So if I were to create a empty stack right now, and I'm going to push something on it, just whatever this value is, 53. Their animations they're using here are going to be using linked lists, but the concept is still the same. So I got one thing in there, 53. If I push 45, remember we're going to push to the top of the stack, so the 45 is going to become the head, and the 53 is the tail. If I push again, 83, remember 83, we're going to push to the top, or the head. If I push again, we're always pushing to the top. No matter what we're doing, no matter how many elements I have, the last thing I added is always going to be at the top of the stack. If I want to pop, we're always going to pop from the top of the stack. Top is 27 here. If I pop, it removes it, returns it, sets the head now to be 83. If I pop here again, 83 is going to be removed. If I pop here again, 45 is going to be removed. And one element left. If I pop here again, it's just going to remove that element. We have an empty list. So conceptually not very difficult for a stack. Here's the operations I'm going to implement. And I'll do it both as a linked list implementation and a kind of built-in Python array implementation. So we're going to push new things to the top of the stack. We're going to pop things from the top of the stack. We're also going to do this peek. Peek allows us to look or peek at whatever value is at the top of the stack. However, it doesn't actually modify it. It's not actually removing it. This comes in handy for a lot of things. So we're still looking at the top of the stack. The only difference between the pop and the peek is the pop actually removes it and modifies the list. The peek just shows us what's data is there, but we're not actually modifying. We're not actually removing that top element. And then this is empty in size, just a couple helper methods to, manage the size, make sure, I can check if it's an empty thing or check how many numbers are on the stack and whatnot. Like I said, this can be done as a normal list in Python or using a node structure and a linked list style structure using nodes. I'm going to do it in both to show you the differences. Doing it as a normal list in Python is incredibly easy. I think each one of these functions basically is one line of code. A linked list is a little bit more complicated, but still not bad. And yeah, like I said, these are used everywhere. If you've done any recursive functions, they work because of the call frame and the call stack. So there's all sorts of stuff that you can implement stacks for. But all right, I'll jump into my code editor here. Okay, so I've already written up the code here. I'm not really going to break it down, or excuse me, I am going to break it down, but I'm not going to sit here and type it out for you. I've got a couple different implementations here. I've got my list stack. This is a stack that uses the Python built-in list. And then I've also got this thing I call the node stack. This is one that it uses nodes in basically a linked list style. I've also got some tests in here that are going to test both of them to make sure they work. If I run my test right now, everything's passing. So to me, both of these are good tested implementations of a stack. So the list stack, let's go over first. This is the easier implementation. This is the one that just uses the Python built-in list. Here's our methods, right? Size, is empty, push, pop, peek. All our operations are O to the one-time complexity. My constructor, because we're using the built-in Python list, we're going to create this private variable called items, and all it's going to be equal to is an empty list. That's it. That's my constructor. Very simple. The size operation, all it's going to do, because I'm using the Python linked-in list, and it's got all sorts of operations already built into it for us. It's a good data structure pre-built for us. If I run the len function and pass in the the list that we're using, that's all I need to do for size. It's going to return the length of my list. That's it. Is empty is pretty easy. In this case, I am actually referencing the size function as well. So I'm saying, hey, go run that size function and see if it's 0. You could do, you know, something like this. Return length of self.items is equivalent to 0. Then if I have to change the logic to figure out what the size is, I'd have to change it in both these spots. So I already got one function that tells me the size. I may as well call that function and use it. And if it's equivalent to 0, is empty is going to be true. So that's it. Again, just one line. Push, adding something to the top of the stack. Again, super easy. Because we're using a Python list, we can just append things right onto it, right? Same thing as if I were to just pull up a terminal here and I were to say, hey, my list is, you know, 1, 2, 3. I can just call append and push a new item onto the end of it, okay? So that's all the append is. Add a new item to the top of the stack. Pop is going to remove the top item from the stack. So again, I can, this isn't, I guess, 3 lines. It's actually 4. So if self.size is 0, I'm going to return none. You have to do this or you'll get an exception. So if I create a new list down here called L, and it's an empty list, and I try to remove calling the pop on it, I'm going to get this error. Index, you can't pop from an empty list. If that's fine, if you don't mind that index error being returned, you don't need this. For my implementation, I just said, hey, if I'm popping from an empty list, I just wanted to return none for whatever reason. Other than that, you just use your built-in link or built-in Python list and call the .pop method on it, just like you would on any other Python list. Peek, same process here. If it's 0, we're gonna if the size is 0, we'll return none. Otherwise, we're gonna use this notation, self.items -1. So if I create a list, now the way the list works in the stack is anything, the last item in the list is basically going to be the head of it. So if I do pop, if I add push, if I add a new node to this or a new element, I'm going to add it to the top of the stack. No, what is it? Oh, it's append. Yeah. So 4 is the top of the stack because that's the last thing I pushed in. So to peek or get the last item that I inserted, or the item at the head, the top of the stack, I just do L -1 as an index, and that's going to bring it up. So you have to do it. You have to do this right here. Self.size is 0, return none, because if I try to index on an empty list, I get that same index error. That's it. That is a stack. Like, it is incredibly easy if you're using a Python built-in list. The linked list implementation is a little more difficult. Here's what it looks like. I just call my node stack, but it just uses a linked list underneath the hood. Linked list style. I've got a first and a last pointer. Both of them are going to start off as none in my constructor, because when I create an empty stack, I have no items in it. So my first and my last are going to be none, and my size property is going to be 0. The size method, all it does is return the self.size. That's it. Very simple, because anytime I add or remove anything in those operations, those methods I'm going to create to handle that logic, I'm gonna update the size there. So I don't need to do anything fancy here, just return that size property. Same thing with the isEmpty. I'm just going to basically go in there and say, is that size property equivalent to 0? That's it. Push. So this is where it gets this is where we get into the linked list style stuff. So to push something onto a linked list implementation of a stack, the first thing we do is we create a new node right here. Okay. Then we have to check, basically, are we working in an empty list? If the list is empty, the size is equivalent to 0. There's other ways to check this. You could check if the head is none as well. But I just said, hey, man, if the size is 0, I know my list is empty. So all we do is we set the first and the last properties to point to that node we just created. And then we're done. Otherwise, if there are other items in the list, we have to create a temporary node and then kind of set that next property as appropriate. So we create the temporary node here, and then we're going to say the new node that we created up here, its next property is going to be that temporary node. So what this is doing, basically, if I have a 1, 2, 3, right? These are things that already exist in my linked list. I have next properties going like that. Okay, so if I want to create a new node, and I'll do this here in pink, this is going to be the new node. That's going to be the new node that I created in memory. The temp node is self.first, so let's create a pointer to that in blue. So that is going to be the head of the list, or the self.first. So all I'm saying here is I say, okay, take that temp node, it's going to be the head of the list. Now in my new node, we're going to set its next property, because right now the new node's next property, right, doesn't point to anything, right? It's just null, none. So we're going to say that new node set its next property to be that temp node. So we're going to create that link there. Then I'm just going to say, okay, the first property on the list, so the first, or the head of the list, is now currently pointing to, let me put a little text here. This is going to point to the head right there. Well, now on this, self.first is going to equal the new node. We're just basically going to shift the head over there. And that's how the pushing works. Finally, once we're done all this, we come down here and we increment that size by 1. We added a new node. We handled all the logic based on if it's an empty list or if there's elements in the list. If we get down here, we know the push was successful, so we just increment our size property. So you can see it's definitely more in-depth. Need to handle some more logic than with a Python built-in list, but overall it's not bad. Pop, basically the same. So we're gonna pop, we have our list here. It's got some next nodes, next properties like that. So if I'm gonna pop, I'd be popping from the head, which is the top of the list here. First thing I do is I say, hey, is the size 0? Because if the size of the list is 0, we're just going to return none. You could throw an index error or whatever you want, but in this case, I'm just going to say it's none. Then I say, hey, if the size is 1, all I do is I set the last property to be none on the list. Okay, because there's nothing left. If I'm popping, there's one element, there's going to be nothing left. Then I go ahead and I remove the first node. So the popped node is going to reference self.first, which is this case is going to be this node here. Then I'm going to say it's the first property is going to be self.first.getNext. My popped node, I'm going to set its next property to none, a bit of cleanup there, and then I'm going to decrement my size. Once I've done these steps here, I've popped the node, I've decremented the size, everything's good. The last thing I want to do is just return the node itself. You can return the node itself, or you can just return the data that's inside of the node. It's up to you based on how you want to implement it. But this is how you would pop a node using a linked list style. Let's see, peak. Peak is pretty simple. You just get the value at the top of the stack. So if our size is 0, we're going to return none. Again, you could throw an index error if you want. It's up to you how you want to implement it. But if our size is 0, I know I have an empty list, so that, it just returns none. Otherwise, we're just going to basically get the head, or the first node, and get the data off of it. And that's it. That is the implementation both for a linked list style structure of a stack, a node, something that uses nodes and pointers, or using the built-in Python array here. Built-in Python list. But there it is. Hopefully you got something out of this video. Hopefully I didn't drone on too long and put you to sleep. So thanks for watching.